Right.
Yeah, the title actually identified is enabling and disruptive technologies for future space explorations. So let me just start the journey with, what actually ISRO has already accomplished. So till today, we have launched 225 launch vehicles and satellite missions altogether, including the foreign actually customers. So 433 satellites together launched, and 55 satellites in orbits. And these are the assets for the country, and 105 satellites in one missions. That was a very actually the very popular and record missions. And if we can see the left side, just 1 minute. Yeah. So left side, this was actually beginnings of our ISRO journey, as we all know that, and our actually the chairman's ISRO, they have the 60th anniversary for Maidan foray into space was celebrated on November 25, 2023. And tomorrow we are launching the 100 missions from Sriharikota with the GSLV Mark II, the F-15s with the NBS-02 satellites. So with this, we have a very far, actually long journey. And we also have many technologies and as well as missions in futures. So if we see today's talk, as today's talk actually identified is enabling the disruptive technologies for future space explorations. So this has three components. One is enabling technology, another is disruptive technologies, another is space exploration component. So first, let me just actually give some introductions on these first two components, that is enabling technologies. What do you mean by enabling technologies? So if you see the definition of enabling technologies is the technical concepts or materials or devices and or processes that are developed in one technology and used in another technology to enable advances, new understanding and applications. So this is the definition of enabling technologies. So if you see when we develop a technology, how do actually we monitor the growth or the progress or the performance of the new technology? So that is given by the famous S curve, because the growth and the maturity actually is in the form of the letter S. So when you say the left side, this is the graph on performance versus effort. When we put an effort to develop certain technology, we have to actually measure its performance in as a metric. Okay. So the first technology, let us say technology A and technology B. So it has initial growth period, then after that it rises, and after some time, even though we put effort, because that performance will not be increased. Okay, so that is called a saturation point. That's called discontinuity of that technology. Then after the new technology will start. So that is called the limit A and B. So now with the examples on the right hand side, we can see that such kind of cassettes, earlier it was very popular. Then after some time, it become actually discontinue, because new technology has come and taken over those technology. So this is called enabling technologies. So we come to the disruptive technologies. What do we mean by disruptive technologies? Disruptive technologies are a class of technologies that can alter or disrupt the market, okay, industries or products by introducing innovative approaches or the solutions. This is very important, how they are different from the enabling technologies. So the most actually the fundamentals and most premier disruptive technology is the invention of the wheel. You will see in here, because before the wheel, people are finding very difficult to move transport okay, from one place to another. But with invention of wheel, because the things have become easier. Now let us see this is a famous camera. Earlier it was a film camera. Now it has been replaced by the digital camera. Then now new disruptive technologies are coming, like let us say the Android phones are coming, AI technology, Netflix. Then the typing machines. Earlier it was there all days. Now it is replaced by the computers. So, and what is the difference? If we see very clearly, you see here in Android phone, we have the Android versions. These Android versions are enabling technologies, while the smartphone itself is a disruptive technology. So there is an overlap here in the S curve itself. So why do we explore? Having understood what is the enabling technology and the disruptive technology, why do we explore? Okay, so the reason actually is there in the famous quote given by the father of the rocket equation, that is Konstantin Tsiolkovsky. He told that the art is the cradle of the humanity, but mankind cannot stay in the cradle forever, because we cannot stay forever in the lap of our mother. So we have to come out, we have to explore, we have to actually face, and we have to live in this world. Okay, so now let me just put what is the global space exploration roadmap and India's space vision 2047. Why 2047 is very important? Because India got independence in 1947, and in 2047 is the 100 years after our independence. So therefore, 2047 is very important. And Honorable Prime Minister termed this is the Viksit Bharat. Okay. So here now, if we see the global space exploration, this exploration map is given by the ISECG. That means International Space Exploration Coordination Group and Global Space Exploration. They released in 2024. This is the latest version. So if you see here, they actually put this graph in year-wise from 2020 to 2050 and beyond. And in three categories. One is Earth-centric technologies, another is moon-centric explorations, another is Mars-centric explorations. And in each actually level, they classify is another is the exploration of orbit, another is exploration on the surface. So lunar orbit, lunar surface, and Earth orbit and Earth surface. When Earth surface, what exploration we have to do? Because we have to develop the analogs, because I think this becomes a very, very important technology nowadays, because in order to explore the Mars, we have to see here actually where the certain ground areas are there where it is almost similar to the Mars terrains. Those are called analogs. So we have to build our technology in establishing the analogs, and we also need to establish the ground infrastructure, because we have to receive the signals from them, and we have to continuous monitoring if we have the human explorations kind of things. Now coming to India's space visions. In the lower Earth orbit, we are having this Gaganyaan famous human space missions, and Bharatiya Antariksh Station means Indian Space Station, which is coming up from the first module will be launched in 2028, and the last module will be launched, will be made operational by 2035. Now coming to the moon explorations. So now see, we have series of lunar explorations, which I'll be covered in the subsequent slide. But if we come to our India's visions, then we have Chandrayaan, we have accomplished Chandrayaan 3. Now Chandrayaan 4 is coming, already approved. Government of India has already approved, and the Chandrayaan 5 will also be coming along with Japan, which is called the LUPEX missions. And in Chandrayaan 4, we'll be trying to bring the sample from the moons, and in ultimately we are attempting to moon landing in 2040. That is what Honorable Prime Minister has announced. Now on the Mars, coming to the Mars landing missions. So we have the Mars landing missions. This is already also been actually in the very advanced study phase. Dr. Praveen, he is well aware because he is the coordinator of these missions. So I will not hang on this much. So this, our India's space vision is in line with the global space exploration roadmap. This is what I wanted to tell. Now space exploration. What do you mean by space exploration? Space explorations is the investigation by means of either crew or uncrew of the reaches of the universe beyond Earth's atmosphere, and the use of information gained for what? To benefit humanity. That is very, very important, because ultimately what we explore, what we go, what we receive, everything that will be for the benefit of mankind. So what are the benefits of human explorations? It has the economic benefits when we explore, like do the minings, let us say the asteroid minings and the moon mining or any explorations, that will be a lot of economic benefits. Okay, so global cooperation benefits, because any explorations we cannot do by one country alone. We have to do like all together in an ecosystems, and we all together will benefit together. And inspirational and societal benefits, like how Chandrayaan 3 has inspired so many like students and citizens in the country and even beyond the country. So this is what when any exploration comes, it always actually inspire many peoples and the science students. And there, of course, there are science benefits, because we have not understood the universe much now, because we are trying to understand and explore and more. There are various types of explorations. One can be, we can consider it as a flyby, because the spacecraft will go and fly near the planet. Then after that, or the oscillation body, then after that it will do some observations, remote sensing. Then after that it will go away. That is called a flyby missions. And orbiter means here what is happening is here it will go in elliptical orbit. Here will be like a parabola in a flyby. So it will not come back. It is one kind of things. Then in orbiter actually will make circles and we can do the remote sensing observations. And another part is lander, because like Chandrayaan 3 we have lander and done the in situ exploration of the surface, and another is the local, because the lander will not move, but rover can move around the surface like a Mars exploration rovers. It has given very important scientific data. And another part is that like copter, that is called like Ingenuity copter of the Mars, which has flown and is much more mobile than the rover. Because if we see the mobility-wise, lander is not mobile, then rover can move to certain extent, but the copter can again actually cover more distance. And of course, last is the crew mission. That is what, because we all know that. And what are the elements of space exploration? When we talk about the technologies, what technology do we need? Okay, in order to have the exploration, first we have to reach there. So we need a propulsion systems. And once we reach there, what we have to do? Because at first we cannot go by human beings. So we have to send the robots. And moreover, we cannot do everything by us. So we need actually robotic systems, manipulators. Then everything we cannot carry from Earth, because if we carry from everything from Earth, the system will be very huge and it's not possible. So we have to use the available resources. What is available there? It is called in situ resource utilizations. And then how to explore, as I mentioned, that there are various payloads are there, like cameras and then spectrum, this one copy method, and rovers and copters and landers. Okay, then after reaching there, we should be safe and sustained. So we need a life protection systems and various protection mechanisms. And we also need the intelligence systems, because what happens is there is a delay from when you go far, there is a delay in the communication systems. So that therefore it should be the cognitive systems should be built. It should have its own intelligence in the systems to take certain decisions on board. And we should send messages that we are also alive, and we are able to navigate the unknown terrains there with what is available. Therefore, we need the navigations and the communication systems. Whatever I have mentioned above, everything needs power, so we need a very reliable power sources. At the end, we ask ourselves that are we really benefiting from these space explorations? So in the subsequent slides, I try to cover these elements as a part of the advanced technologies. So if you see the renewed global interest, I mentioned that because you see globally, people are focusing on more on exploration because we want to explore the nearby celestial bodies, and most probably the moon and the Mars and other actually moons of other our planets. So if we see the NASA program, this we know that they are trying to land on the moon after 1969, the moon landings. So they are having huge programs of Artemis programs, as well as we are also signatory of these Artemis programs, and they are trying to build a gateway. Gateway is the like international space stations, which is built around the moon. Okay, so because from that only the human landing will take place, from that space stations which is around the moon, that is a gateway. So our Orion spacecraft will go and dock there and stay there. Then astronauts will go and land on the lunar surface and come and dock it. Then after that, Orion again will come back. This is their technology. And China is also having, China along with basically Russia, they are having an aspiration of establishment of international lunar research station as a series of their Chang'e missions. So the Chang'e up to that 6 they have accomplished. From after Chang'e 8, they are trying to build these stations along with the they also have some other collaborating countries. So ISA is also having, because as we know that when we go there, because specifically for the crew missions, we have to have the communication navigation structure. So the ISA is taking these programs very seriously. Then of course SpaceX is leading that he is trying to make a self-sustaining colony on Mars, starting with a small initial crew and expansions. We do know that starships and those things is in a great trial stage. And of course the last one, that is the CLPS, is a very interesting program. That is the commercial lunar payload services, because NASA is promoting the American companies to send to develop small landers and rovers with to say make future explorers. Okay, so in these programs, anybody can actually make landers and rovers. They will be the finance will be given. Then after that, they can try along with NASA to send to land on the moon. So the CLPS 1, the mission failed, but the CLPS 2, it was intuitive missions. It was a success. So like that, only there are a series of up to 2028 that they have these programs. So if you come to the propulsion systems, these are the basic equations, because all these propulsion systems are based on these basic equations. It will have different formulations. So when you say that the object in equilibrium, means Newton's first law of motion actually the holds good. That means they are in equilibrium, means all the forces are in, they cancel each other. Then what is happening in this? Here, this is a rocket. When there is an unbalanced motions, that is called the second law of motions. Then after that, what happens is it starts moving. So here, what is happening? If it is a closed system, then Newton's third law of motion, and they applies that. So in this is a rocket body. This is a nozzle. So when the fuel, this is called a propellant, fuel and oxidizer, they are mixed because it is a combustion process. In a combustion process, we need oxygen. So oxidizer is very important, and oxidizer is common for everything, and fuel only will keep on change depending upon either is a solid fuel, liquid fuel, or cryogenic fuels and all those things. So the solid and the propellants will be actually burned in a combustion chamber. Then after that, that exhaust gases will be sent through a nozzle, so it will expand suddenly. Okay, so there is a change in the ratio. So this is the thrust which is produced because of that one. So thrust depends upon the mass flow rate and exhaust speed. Then after that, difference in the pressure exit and the pressure that in the outside this area, and then multiply the cross section of the nozzle area. So because of this thrust, then it starts moving with certain velocity, that is the delta V. So depends upon exhaust velocity and the change in the mass ratio. So what is happening is, when the change in speed is directly proportional to exhaust speed, and exhaust speed also is related to certain parameter called specific impulse in BE by G. So it is the change in speed also, that means actually the gain in speed can be written in terms of this equation as well. So if you see the rocket propulsion, there are various propulsion. I told you that solid propellant is also there, solid propulsion mechanisms wherein the liquid and wherever fuel and oxidizers are in the form of the solid, and a liquid propellant means wherever the liquid and oxidizers, they will be in the form of the liquid. But here they should be mixed together so that they will burn in this combustion chamber. So to mix together, so different systems can be used. Either is the pump system can be used, or otherwise the pressure systems can be used. That is, if pressure system is used, that is called pressure fed. If the pump system is used, it is called the pump fed. So here, mostly commonly use the liquid, liquid oxygens and liquid hydrogens and liquid oxygen and the methanes. So these are the like almost the workhorse of this today's rocket propulsions. In terms of advanced technology, let us say this electric propulsion is very, very important. I want the students to take up certain actually the projects in these areas, because electric propulsion is the future of the like electric vehicle nowadays. So like in space also, electric propulsion is the future of this technology, because of certain advantages that I will come into the next slides. So in this electric propulsion, there are different variants are there that the student can study. Like suppose that let us say our um, the pulse plasma thruster is also there. Then ion grid method is there. Okay, then that ICT is there. So like the Bessemer technology is there. So different variants are there, but working principle is same. So in electric propulsion, what is happening is the fuel is a neutral atoms. Okay, so this fuel is a neutral atom. So there is these neutral atoms. Here, what happens is combustion is not taking place. Okay, so here neutral atoms. Neutral atom, you know that they are neutral, so they will not be acted upon by either electric or magnetic fields. Then what is happening is this, using an electron gun, they will be actually ionized. These neutral atoms, here is a green, so they'll be bombarded with electrons, they'll become ions. These positive ions in the electrons, then they will be separated through some, like by applying electric fields. Then these electric fields attracts the opposite this one, the ions. Then after that, they'll be going through this with a very high speed. Okay, so with that exhaust speed, then after that the thrust will be generated. That is what actually the previous rocket equation actually tells, that the exhaust speed is very, very important, because the thrust, whatever is produced, is directly proportional to the exhaust speed and in terms of the specific impulse. Okay, so that way actually the thrust is obtained here. And one is a solar cell. This is it's a very big area depending upon the pressure, the radiation pressure of that it has to cell. These are all for interplanetary exploration, not for the rocket lifting. And I must tell you that for lifting a rocket for initial stage, it should be done by the solid propellant only, because the thrust should be very high to defy the gravity, because the gravity is almost 9.8 meter per second square. So the gravity of these tons of the very heavy rocket, you have to live, you can live with only with the thrust generated by the solid propellant. Then after that, liquid propellants and all those things can be done. So it's not possible that, so when we have an electric propulsion, it's not possible to lift a rocket in the initial stage itself. Electric propulsion will be especially useful when you travel in the longer in the interplanetary explorations. Okay. So and for the present situation, we are using for like for small the vector chains, thrust vector chains, as well as the north-south station keepings and east-west station keeping. Another very important technology is the antimatter propulsion. Antimatter propulsion I'll cover here because of the lack of time. Then I'll coming to the next slides. And another very advanced technology, nuclear thermal propulsion system, that is called NTP, which actually USA also has worked very rigorously in this. So what does it do is, here is the same thing. The propellant is the liquid hydrogens. These liquid hydrogens, when it is actually pump fed, I told you that two are there. One is a pump fed, another is pressure fed. It is fed to this combustion chamber, that is a reactor core. Here, what is happening is they should be heated up because this hydrogen propellant should be heated up. That heat is derived from the that thermo, actually the radiation, that is radioactivity heat, because radioactive source, when you have they actually disintegrate, they generate a lot of heat. So that heat is used to heat this hydrogen propellant. Then after that, they will be heated up and they will expand as a gas to this. So hydrogen is commonly used because they give a very high, around 900 seconds kind of ISP as compared to water, which gives only 325 seconds. So this is a very important area which students can take up as in projects in their either BTech or MTech. And coming here, antimatter propulsion is very, very advanced technology. And one day, if it is realized, this will be the only technology which will shape human beings, because to go to Mars, from now, the existing the conventional fuel propellants can takes 11 months. But with this, it can actually go to Mars in a week time. So this is the only propulsion system. If it is realized later on, it can save the human race. So what do we mean by antimatters? Antiparticles actually look like, behave like the corresponding matter particles, except they have the opposite charge. So if we see this is a normal matter, that is a proton is inside and electrons are revolving around the nucleus. But here, what is in an antimatter? Antiprotons will be inside the proton. They have the negative charge because the proton is positive, and here a positron, that means anti-electrons will be revolving around the nucleus. It's not like the nucleus is revolving. The nucleus is there only at the center only, but this anti-proton, anti-electron means that is positrons will be moving around the nucleus. Okay, so they are produced in very high accelerator like kind of CERNs, and they are generally stored in the penning trap. That is all. These are penning trap, and this is an accelerator. Penning trap means these are because matter and antimatter cannot touch each other. This is what is happening is from where the antimatter energy is derived means whenever matter and antimatter they touch each other, they annihilate each other. Okay, so in this annihilation process, this is also like you can say it is a conversion from mass to energy. So this conversion process, there is no residual mass left. So it is complete conversion of matter to energy. So in this process, there are two photons are created out of 0.51 MeV, and total two photons multiplied by 2 will give around 1 MeV. So this is the highest, like even in terms of our the energy density is compared with any other propellants. So now, earlier actually, because of this difficulty in the productions of these antimatter particles, as well as the large number of antimatter particles as the storage, there was a limitation. But in 2008, actually these two scientists called Chen and Stenson, they came up with a very breakthrough discovery that they are able to produce very good numbers of the antiparticles, okay, particle and antiparticles, and then after that they're able to store in large amounts of this for quite some time. So based on this, they propose a matter and antimatter propulsion systems. Here, this is the nuclear fission reactor. Then after that, we need another, because there should be a source required and a particle generator is required. That is a particle generator here. Then the particle generator should be, again, once it's generated, you have to collect it. So once you collect here, particle and antiparticle, they should not be touch each other, because particle has to be collected in separately, and antiparticle has to be collected separately. So once they brought in this such kind of combustion chamber, they will annihilate each other, and a large amount of energy is generated. So with that, the delta V can be generated. Okay. So these are typical examples of these matter and antimatter spacecraft. Considering a 10-ton of spacecraft with electron-positron annihilations of the 6 × 10⁻17 pair particles, they can have an acceleration of 2 meters per second. 2 meters per second acceleration is very, very small one if we compare it. But from physics, we know that once we have an accelerations, so with time we can have the speed, because V is equal to U plus AT. So we have such kind of with time this acceleration, because of the acceleration, they can give a very huge amount of speed. Up to 40% of the speed of light is achievable. So with these 10 grams of antiprotons, I have mentioned earlier that we can go Mars in almost in a month time or week's time, than instead of the 11 months of conventional propulsions. So with this, we can even propel that. Scientists have proposed that we can even go to the Alpha Centauri, that in 40 years time, that is within the human lifespans of around 100 years. Otherwise, with our um, conventional system, is not possible to go to Alpha Centauri, which is approximately around 4.3 light years away from here. So let me just summarize it very quickly, then we'll go to the next one. So LOX, methane, electric propulsion, nuclear thermal propulsion, antimatter propulsion, these are very, very advanced propulsion systems. And the LOX methane is means liquid oxygens, and methane is commonly used because of this availability and higher energy, because at present this is the workhorse, and this is also coming up now, and these two are futures. Okay, so students can work on this and like you may be knowing about this one, like our Starlink, the SpaceX, they all are actually having these electropropulsion systems. And Starship is a LOX methane, because it is. And LOX methane, the beauty is when you go to the Mars, we can generate this methane, that I'll come into this one. So students can take up these projects, because these very, very important the areas for futures. And coming to the robotics, because I have mentioned that when you go to any unknown places, because we don't know the environments, because everything what we know and what we reach there is really the difference will be there. So robots are very, very important, because we cannot touch the things by hand, and we cannot simply go out. We have to do the experiments. Robotic manipulators are there. What is the radiation level, and how safe we are to go astronauts out. Then all these things are very, very important. And moreover, when we go to long journey, then we need a certain actually the company, like suppose this is kind of companion robots are required, and moreover they can do certain tasks also, such kind of smart enabled free flyer, actually the robots are also required. So when coming to the robot, because there are various types of robots, we know what together we have seen is only the wheel robots, like Chandrayaan 2 and 3, also the wheel robots, they will move the wheels. Okay, so there are certain class of the robots that is called the leg robots. Like you might have heard that in the recent 26 January, that in the parade there was a dog robot. Okay, with this that is called the it was display, so it was moving also. So these things are very, very important, because it has the 4 legs, and it gives a better maneuverability. And moreover, in the soft terrains, leg robot is having advantages, because in the hard terrains, wheel robot is faster. So there will be certain advantages and disadvantages in both. But if we combine it, we can get actually both advantages. That is what we aspire to do in future. Okay. So, and biomimicry is very, very important in robotics, because many things nature gives us a solutions to our difficult problems. So that way, so this is actually one area where I mentioned that both leg and robot, the wheel robots can be combined together, and we can call as a reconfigurable rover. Here, reconfigurable rover in the sense that it can have rolling as well as crawling motion. So you can see here, this is one spider. Okay, so this spider is in a Morocco desert. When they are provoked by certain danger, then instead of going by normally, they will go with the cartwheel motions. They will jump and like this go away. So then after that, so inspired by such designs, such kind of rovers can be designed. Okay, so these are works in under progress. Then with this, now we can see here, you see it can roll, and then it can crawl, it can change the gait, and it is with this is very, very efficient to navigate certain terrains. Like, let us say, in terms of the planetary craters, because planetary craters gives a lot of opportunity for us to understand the evolution of, because the craters will have the stratigraphic studies, because all the layers can be studied, okay, one by one, because craters walls will give the different layers based on the geological evolutions. Okay, so that is one part. Another is craters are having the permanent shadow regions. So since they are permanently shadow regions, there may be some actually the signs of the life, earlier life, either extinct or extends. And moreover, these are very, very important. So, and but they are quite difficult to explore it, because the slopes are very high, and it is quite unstructured and very complex. Okay, the temperature is very low with the available now electronics, whether it will survive or not. These are actually some of the things. But we need to develop new technologies. So when we show about the crater explorations, it can be done by the remote sensing, spacecraft, in situ exploration analysis, lander rover, and lander and rover sample returns, and crater wall actually climbers are the ultimate solutions, because they can go there and interact with such kind of walls, then see that, and we can do the in situ like analysis of those I'm telling different layers, that geological layers. Then we can see like what is the signature there. So coming to the crater wall climbers, it is not new that different actually space agencies are developing. So this I want to tell that students can take up these different projects and make it develop in the country itself as a part of their that like their BTech or MTech or college projects. So this is one Scorpion projects. Okay, the NASA has developed it. It has many legs. It's around 8 legs are there. 1, 2, 3, 4 here. This side also 4. So it has various degrees of freedoms of the movements, and the such kind of things. The distinct part is they have the decentralized mechanism, because this leg alone can move it instead of moving the all together. Okay, so these another space while climber developed by ISA. So they are having such kind of, you see, they can climb the slopes. Okay, so this Aramis is another developed by ISA, different configurations, different company, and another is also developed by Cesar is ISA. So they are having such kind of, you see, the wheel kind of things, the pedaling wheel kind of things, so they can go to the loose soils structure. And this snack board is very very interesting, because when you go to the fissure kind of things, no, that let us say the lava tubes, these are very very important here. This is one teeter. So from the mother rover, you can do such kind of the daughter rover through one teeter. I mean, it's like a electric wire or data to transfer the power as well as the data. Because in this snake, we cannot put everything, the power, everything. So it has like a umbilical cord. Everything has to be provided by the mother rover. Then after that, mother rover will send a daughter rover. We'll put one camera here and light. Then we'll go inside the fissures or the lava and see that what signatures are available. Okay, this is very very important and interesting. So this can be developed by the students, and it will have a lot of applications, even actually for analog conditions in on art itself. So one is the nonocot. This is also like our JCB type. So they can go with these wheel designs or the war tank designs. They can go negotiate different terrains. Okay. So now coming to the concepts of the in situ resource utilizations. So as I mentioned that we cannot take everything, all resources from here when we explore, do the explorations of the very far actually planetary systems. So we have to use the available resources there and make use of making certain our habitats or structures there. Okay. So in this regard, let me just mention about, because there are certain three primary steps are there when we talk about the concepts of in situ resource utilizations. One is the resource assessment. First, we have to assess the resources. Then we resource acquisitions. Okay. Then resource processing. So in, let us see here, if we should see the moon, no. Then these lunar resources I mark here 1, 2, 3, 4, where the regions are there. These are the polar highland regoliths. Oxides of aluminum silicons are actually abundantly available, which is where the Chandrayaan 2 and 3 have landed there. Okay. Then number 2 is the our near the south poles, because polar ice and volatile will be available. Then number 3, such things are these are the ilmenite and pyroclast glass. Okay, these are the minerals. Then number 4, the rare earth and the sunlight is also plentifully available. In the resource assessments, we have done it. Let us see the Chandrayaan through the remote sensing and through the local lander and rover. We have done it. Now request resource acquisitions, we will be doing it in the next missions. Then resource processing. So I'll just come up here. To certain extents on ground, we have done this exercise. Okay. So resource initiatives, if we see the resource mapping, you can see from here. Chandrayaan 1, we already have detected the detection of the hydroxyl, that is the iron mineral pyroxenes, wherever red colors are there, pyroxene 1. Hydroxyl is the blue color one. So the our moon mineral mapper, so already detected the water, and the MIP. Okay, this is the moon mineral mapper, this one. Then MIP, this moon impact probe, has detected water. And Chandrayaan 2, we have actually mapped all the craters, almost all the craters of the lunar surface. And the Chandrayaan 3, we have detected, we have two payloads in the rover. That is the LIPS, laser induced background spectroscopy, and another is APIX, that means alpha particle X-ray spectrometer. They have mapped the elements, various elements on the lunar surface, and it is in line with, let me just tell you later on that it is in line with the lunar simulant. There is one lunar simulant, I don't know whether you are aware of that. There is an area called the Sitampundi anorthosite rock complex in Tamil Nadu. So this rock is very, very similar to the lunar regolith, which is available on the surface of the moon. So this is the 1:1 comparisons between the Apollo 16 and as well as the lunar simulant. And is also, they are very, very similar, as well as here also the compositions. When you see the aluminum and the silicon, here also you see most of the things will be available. So that I think probably this is strength only. I have okay. Here it is coming here, silicon oxide 45%, because silicon oxide and titanium oxide, that is what we have in aluminum. So abundantly available. If we see here, aluminum and silicon is abundantly available, as we can see from here also. So 45% is silicon oxide, and almost aluminum oxide is 26% in the highland regions. So this is very important. And here I will show you one. Yeah, this one. This is one the space brick, which is made in association with the Indian Institute of Science, using a very environmental friendly process. Okay, so okay, there is one video here. This is machinable, means it is quite actually the strong. Okay, so the compressive strength is almost a 5.5 megapixel. That means this is as equivalent as the in the polar regions, you know, the ice, there is one igloo structure. So it is almost that strength. So that is quite good strength. So ISRO processes, there are very ISRO processes are there in situ resource relations. Then from the lunar regolith, oxygen can be extracted. This is from the moon, for moon I'm telling. So there are chemical process, electrolytic process, pyrolytic process, and it is the comparisons of this one. So the elamide reductions using hydrogen can be done. Then carbothermals, or using reductions with the carbon. Okay, one is a molten electrolysis, means you heat the regolith and become the molten state above 1400 degrees centigrade. Then vacuum pyrolysis means again the same thing. So you also have to hit that one. Then after that, what happens is, because once you do vacuum pyrolysis, once you hit, no, then after that, these metals and metal oxide will be condensed. Okay, then oxygen will be taken out separately. So the oxygen liquefaction is required. Then these condensations, again we have to take out these metal oxides. Okay, so this is the process. So out of this vacuum pyrolysis for oxygen synthesis more feasible as compared with the others one, because of this more green ticks. Okay, and for the Mars mission, for the Mars missions, Sabatier reaction is the key, because when we want to make use of this carbon dioxide, because carbon dioxide is almost 97%, that is above 90 actually in the Mars atmosphere. So carbon dioxide should be used, make use to generate the methane. Okay, so through the Sabatier reaction. So we have the carbon dioxide there. Then we'll actually supply hydrogen from where? Because from the Mars regolith will extract that water kind of things. Okay, so this water, once we do that regolith processing, then water extraction, Mars regolith, from that we'll process the regolith, water will be extracted, that water will be electrolyzed. Once water is electrolyzed, the hydrogen which is produced from there will be fed to the Sabatier reactor, and then after that the carbon dioxide and hydrogen will be mixed together, and then methane is formed. Then water is coming, again will be actually in the closed loop will go. Then it once again electrolysis will be done, oxygen is separated, hydrogen will go there. So in this process will continue, and these methane and oxygens both are very important, because I already mentioned that LOX methane is the best, because whenever we go there. So this in situ resource relation, LOX methane is very, very important, the technology for, and moreover, you may be knowing that recently in a MOXIE experiment, NASA has already demonstrated extraction of oxygen from the carbon dioxide on the Mars surface. So, but that process is not the Sabatier reaction, that is the electrolysis process. Okay. So now communications and navigations, you know that when you go very far, it is very difficult to communicate from Earth, because this whatever the signals are there is actually, the thing is, this is a lunar PNT, then this is our this is Earth. Okay, so therefore the signals become less and weak, as well as the strength is very poor. Okay, because of the spread. That is what I'll make here. So therefore, now different people like NASA and ISRO, they are making the lunar constellations, and PNT means position, navigation, and timing the constellations. So coming to the communications, they should have real time. They should have the very low latency communications, and we all in the future, when we say that the communication, we focus on the quantum communications and optical communication because of certain advantages. Because optical communication gives a very good advantages here as compared with the RF communication. This is here, if you compare RF and optical communication in the Mars to Moon Earth communication, you see here this is divergence, because when you put a torchlight, the beam will diverge. So the similarly, so the when you actually send a beam of RF signal from the Mars, so it diverges in almost 100 size of the Earth diameter. It's not possible to keep a antenna of this diameter. But if we consider the optical link, because the diameter will be, this beam width divergence will be very small, because the beam divergence is proportional to lambda, that is the wavelength. So for optical, if we see the spectrums, their wavelength is very large. Okay, so therefore there are certain advantages in terms of optical communication. In terms of, let's say, data rate will be very high, so we can actually during certain period the visibility, we can transmit large amount of volume because the data rate is very high. And they also have, it is called a swap, that is size, weight, and power. They have a very less as compared with the RF communications. And antenna size, most important is because of this less beam divergence, their antenna size will be very small. Okay. Now it will not be complete without touching the quantum technologies, because quantum technologies is the future of technology. So quantum technology can be divided into 4 verticals. One is quantum communications, and another is quantum sensing, and quantum computations, and quantum materials. In quantum communications, we have the fiber as well as free space communications. Why quantum is required? Because quantum communication is very secure. Okay, so when we terms of the security, we have to do the quantum communication. When we talk about the speed, we have to do the like our the optical communication. When we talk about let us say the rain fading and all those things, we have to see the RF communications. Okay, so there are different things are there. So quantum sensing, because quantum radar and quantum atom interferometry, these are the because they have a very enhanced sensitivity. They can sense the signal against the background noise. Okay, quantum computation speed is very fast. That is called the quantum supremacy. Whatever the classical computers cannot do, quantum computers can do in a very less time. So quantum material means you have a lot of materials which can actually tune, okay, their properties, so that their potential will be harvested very efficiently. So coming to the quantum communication, because as compared to all other particles right now in the world as well as in our organizations, quantum technology is the matured technology. Okay, so we have demonstrated also 300-meter free space. That was the first in the country. So coming to the quantum communications, so there because when you show the communications, one party has to communicate to the other party. Okay, so that party he has to send some data. Okay, that is a transmitter receiver. So in quantum communication, in classical communication, we are having only one channel. Okay, in quantum communication, there are 2 channels, because one channel is used to send a key. Okay, because when we send communications, what happens is I want to send some certain communications which I don't want to reveal to anyone. I want to reveal only that one, because when let us say I talk about sending a letter to the suppose to another person, the postman should not open the envelope and then read the message, correct? So then if he reads a message, then it's called he has tampered, as well as he has that is called in technical language, is called he has eavesdrop. Okay, so in order to avoid such kind of stealing the information, eavesdropping the informations, these in quantum communication, these two channels are actually separated. In this quantum channel, only the key, because when I send a message, that message should be encrypted like a password. So that password is the key. Okay, so that password will be sent in a separate channel and not along with the message. Then the password will encrypt the message. Then after that, it will be sent to this public channel. So then again, the password will be communicated separately to this receiver in a different channel, that is called a quantum channel. So in this way, since you are not sending together password, that means key as well as the lock, you are not sending together, it is secure. But how do we, because similarly it is secure, but this quantum communication, the challenge has come because of the advent of the quantum computers, because right now the keys are generated using the factorization of the large numbers. Okay, so this with the advent of the quantum computers, this factorization becomes it takes very less time as compared with the classical computers. So otherwise, this classical communication is also equally secure. But in quantum communication, the fear is because once the quantum computer comes into the picture, because there is a chance of being hacked the key and it is no longer secure. Okay, so in this there are certain protocols are there, and moreover quantum communication is inherently secure because of the certain quantum laws that is called Heisenberg's uncertainty principle, then quantum entanglement, no cloning theorem. These are the three bases of this. So when we hear what is happening is in the quantum channel, key is generated, and now with that key, the data is encrypted and sent in a classical channel, and these two parties will have the in this process of generating the key, because they will have the same key. Okay, that is called a symmetric key. And whatever we are using nowadays, you might have seen in WhatsApp also, like communication is end-to-end encrypted. That is then the WhatsApp communication is not a quantum communication; it's a classical only, but it is a non-symmetric key, that is called a public key crypto systems. But in quantum communication is called a symmetric key systems. So quantum communication has certain actually applications. Okay, so in terms of let us say the strategic communications, when we cannot compromise the security of the informations, then when we want to communicate that data over large distance, we have to use a satellite-based quantum communication. Banking services, because OTPs are very, very important. OTP cannot be shared with anyone, so OTP can be generated. And in NAVIC the configurations, then also key also can be generated. And government and defense industry, so there is a lot of like applications. So it is very, very important area. And it has many applications like your single photon, then entanglement photon. Students can take up these projects, and their labs are available, like Thor lab, where they can purchase items and assemble and demonstrate in the lab, because this is the future of the communication technologies. So quantum communication, satellite-based quantum communications. So I must tell you, this is the architecture that this is called the BB84 protocol. That is Bennett and Brassard in 1984. They have proposed this protocol. And the BBM92 protocol means Bennett, Brassard, and Mermin. Three scientists' name they proposed is in 1992. Okay, so therefore the name is given like this. So in the BB84 means it is single photon. So the satellite, these are ground stations. When satellite passes over this ground station, he will transmit a key here that is called the ground station A, that is KA. Okay, so when the satellite passes, then above this ground station again he will transmit another key. So but the satellite is having both these keys, KA and KB. Okay, so now after reaching this ground station, after transmitting this KB, again he will do XOR operation of this key and transmit again same to the ground station. And this ground station person, he will do XOR of this key, whatever the key he has. Okay, KB XOR with the KA, AB XOR. Then after that he will get his KA. So without asking this station A that what is the key, then station B also can have the same key by doing this XOR operation with the help of the satellite. This is how actually the symmetrical key is generated, and they know that now once they know the symmetrical key, whatever information this person has sent without asking to this person, he can decrypt it. Okay, so in this BBM92 protocol means is a quantum entanglement protocol. So the satellite is having one entanglement source, means that he will generate from one photon to actually entangled photon, means these two are entangled photons. Okay, they are in correlated and the superposition state, and these entangled photons he will send to this ground station A and ground station B separately. In this process he will generate the key in such way that both will have the same key. Okay,
only 2 minutes.
Yeah, I'm winding up. Yes. So these are the human centric and life support systems. There are various components are there. I mentioned that when you go there, we have to have that is like environmental control life support systems. And for like there are two types are there. One is non-generative and another is regenerative. Like spacesuits, you may be knowing that the astronauts are having spacesuits. Those are called life support systems, and they have different components. And these are very good areas where students can do the projects in their colleges. They can develop like air revitalization systems, thermal and humidity control, cabin pressure, food and water, but personal hygiene, how to design a toilet itself is a very big actual challenge. And a Sabatier reaction is also important. And oxygen generation systems from our exhaled carbon dioxide, how the oxygen will be generated, and the urine and the water, how it will process. Okay, these are very, very important, can be taken as a student's project. Then this is the last, Dr. Praveen. So, and one power source, I told you that when we go to the space exploration, temperature is very, very low. So that temperature, the normal actually lithium ion kind of sense will not sustain, because they can operate only from 0 to 40 degrees centigrade. This is how they discharge characteristics. So there are certain low temperature electrolytes are there with the formulate. They can go up to actually work up to minus 40 degree and below. These are actually, I have come across various such kind of things after reading so many papers. So I thought that it's good to share with the students. They can take up such kind of challenges, works in the low temperature the areas. So these are the characteristics. So this is one. This is lithium ion. That is HP, means actual high power cell. So 1865 the configurations. Okay. So they means such kind of things. Means 18 is this one. And the round cylinder, and 65 the length. Okay. 0 means it is a cylinder. Okay. So this is the notations. So what is happening is they can sustain up to very low temperature. They can up to 30 ampere of that capacity, it can discharge it. Okay. So this is one special, this one developed by NASA. So in that you see low temperature cell can sustain the temperature you see up to minus 40, it can sustain the capacity almost 85 to 90%. But ordinary cell, it will drop into 0. So they cannot sustain it. These are area, and another is the rollout solar array, which is very, very important when we explore the, let us say, I told you the making of the space station around the moon space station, around any celestial body. So this is kind of rollout solar array is very, very important. This is the only solutions. Even International Space Station recently have inducted, as well as they have all these are International Space Station rollout solar arrays, and they also have implemented in this DART mission, that is double asteroid redirection test. You may be knowing that these asteroids, the spacecraft will go and bombard and change their directions. So this is the future of the solar array technology. Students can take up the projects. Then so at the end, also I would like to actually end this talk giving you the lot of opportunities that we have. Students have various areas where they can work as a project: antimatter propulsion, electric propulsion, reconfigurable rover, swarm rover, snake boat, optical communication, self-healing materials, quantum technologies, entanglement swapping. Because when we do the quantum internet, you need entanglement swapping. Okay, RHU and RTG, and due to the lack of time, I cannot cover it. And the thermocouples, because when you from from RHU to RTG, radioactive heating unit, to radio isotope thermoelectric generator unit, thermocouples and Stirling engines. Okay, thermocouples will have around 6% efficiency. Stirling engine will have around 25% efficiency. So both can be, recently China has demonstrated in their space station. Okay, so the Stirling engine is very, very important area. Student can work. Low temperature battery. Rectena is where the, like, you convert from the DC to the AC. Is it Rectena, space-based solar array, roller array, and many more interesting areas. Okay, that's